So let's talk about heat transfer. This part's kind of fun. This is just heat transfer mechanisms and how they're used to cook things, I guess. Conduction. Conduction is just basically fire heats up pan heats up food. We'll talk about what happens on the microscopic level in a minute. Convection, fire heats up air, right? Air rises when it's hot and then replaces the cool air falls, and then that creates something that looks like this. Oh, yeah, there it goes, like that. And then radiation, okay? Electromagnetic radiation, although technically all of these are radiation. What kind of radiation is this? Infrared. So you know that whole electromagnetic spectrum thing, right? What do we see? Colors, yes, visible light. Okay, so visible light, that's the middle of the spectrum. If you go in the violet direction, right, you get ultraviolet, and then you get X-rays, and then you get gamma rays. Okay, if you go in the other direction, you get to red, and then you get infrared, and then you get radio waves, and then you get microwaves. I think it's that order. But those are longer wavelengths, lower energy. If you go this way, it's shorter wavelengths, higher energy. Okay, and which ones are dangerous?
Yeah.
Gamma's pretty dangerous, yeah. Where's the cutoff? So when people are like, radiation is scary, they don't know they're not being specific enough. Okay, because there is some radiation you should avoid. Like, for instance, why do you wear sunscreen? UV is not great. Okay, UV, X-rays, gamma, you want to limit your exposure to those. Why? What's special about that energy cutoff? What does it do? No, microwaves can cook you. You just want to get hotter. Well, yeah, it's dangerous to be in a microwave, but it's not really dangerous to be near a microwave. Well, why do you think that radiation is dangerous? Like, what does it do?
I mean, there's different things that radiation does, like it changes.
Messes up your atoms. How? So it turns out anything UV and above is called ionizing radiation. What does ionizing mean? Yeah, it rips up an atom, basically. It takes apart, either it takes a positive charge off or it takes a negative charge off of an atom, making it an ion. Most atoms and molecules are electrically neutral, meaning they have the same number of positive charges as negative charges, so they don't really interact with things around them because they don't have a lot of mass, so they can either bump into things, but there's a lot of space between atoms, so, they don't do a whole lot. If you have an ion, it's positively or negatively charged. And when we do Physics 200, you'll see the forces of charge are much, much bigger than the forces we deal with from gravity and other things, okay? And charge is the most common force. So if you ionize, usually water, okay, all of those things ionize water, and we're made of a lot of water. Just charged water molecules floating around, not that big of a deal. But when the water molecules come into contact with other atoms, now they're going to interact with them. So if one of those water molecules comes in contact with some of your DNA while your cells are replicating, or whatever it is that cells do, because I don't know much about biology, they can rip apart pieces of your DNA. And sometimes that's not that big of a deal. Either you have some RNA or whatever that stuff is that fixes it, or the cell just dies. But once in a while, it screws up the replication process in such a way that the cells don't know when to stop making more cells. And guess what we call that? Cancer. Okay? And the more times you ionize the water in your body, and that might interact with the DNA, the higher the probability that you'll get some sort of cancer, because it's just a roulette game. And there's enough players in that game that the statistics are nice and linear. So more radiation exposure in the ionizing range, right? The chances of cancer go up linearly, which is, I guess, nice because you at least know what your risks are. But, microwaves are not going to do that to you, okay? Visible light is not going to do that to you. Get into UV, the reason it's dangerous is because there's an actual biological pathway that makes it dangerous. Anybody that says, like, using your cell phone is going to give you a brain tumor, they don't actually have any evidence that that's true, I mean, at most, it might slightly warm up your brain a little bit, but not that much. And so there's not really any good data that says that like microwave and radio waves hurt you. And we've had radio waves and microwaves floating around for a long ass time now, and it's not, we have a lot of evidence if there was something going on. But we're 100% sure that ionizing radiation can hurt you, okay? And we have lots of evidence that it does. And just for scale, right, when you're going for, this is why like going and getting a CT scan for funsies is a bad idea, okay? When should you get a CT scan? When should you get an X-ray done? When you need it. When the consequences of not doing it are more dire than the risk of doing it, okay? So make those decisions wisely. Turns out MRI doesn't seem to have a lot of long-term risks. So if somebody wants to give you an MRI for fun, sure. But no X-rays for fun, which is great, because when they invented the X-rays, people would just like take X-rays of themselves for fun all the time, and they used way more dose than they needed because they didn't know what they were doing, and lots of people got all kinds of fun cancers for fun. You know the Curies, right? So we're going way off topic now. So Madame Curie. Big deal. She's a lady that did physics, and she won 2 Nobel Prizes, blah, blah, blah. Okay. Everybody's like, yay, Madame Curie. She had a husband named Pierre, also a smart guy. And they discovered radium together. Mostly she did, but he knew about it too. And so he would like walk around with radium in his pocket, and they like handled it with their hands. Like they're just like picking up radioactive stuff and being like, how cool is this? But to be fair to them, this was the first radioactive stuff anybody had really dealt with, so nobody knew that it was dangerous. They were like, it's glowing, how fun, rub it on your face. So guess what killed Pierre Curie? Yeah. No, he got hit by a truck. But it was probably because he had severe bone cancer at the time and was moving very slowly and couldn't see very well, because he was just, like, we didn't have the diagnosis back then, but he was probably riddled with cancer by the time he got hit by the truck. Maybe that was more of a godsend. Anyway, but it's a fun punchline, right? Okay, so conduction, all right? Temperature difference causes thermal energy to flow from hot to cold. This is when you're dealing pretty much with solids, okay? So like a metal pan, for instance. And here's a beautiful animation. Here is your source of heat. And here are some molecules of a solid. Yes? Okay. And the heat does this. It jiggles these molecules, which jiggle these molecules, which jiggle these molecules. And jiggling molecules mean heat, okay? Because temperature is just microscopic kinetic energy. So if you have a temperature that goes up, it's because the molecules went from going like this to going like this, okay? So fast-moving molecules mean higher temperature. All right, slow-moving molecules mean lower temperature. All right, and anyway, thermal conductivity, that's how quickly materials conduct heat, so that's heat conduction. Guess which things make good conductors? Well, silver is better than copper, but once again, why are our pots and pans not silver? Because it's expensive. Yeah, and also it tarnishes really easily, although so does copper, whatever. Concrete doesn't have great thermal conductivity. Silicon has pretty terrible conductivity, which means silicon makes good oven mitts. Yeah? And also some other things. And then air actually has pretty bad thermal conductivity. Water doesn't have great thermal conductivity, but it's a lot better than air. And that's why you can hang out in 45-degree air for a long time, but 45-degree water can kill you in a couple of hours. Because your body just can't keep up with keeping you at the right temperature for you to not die. Okay? Rates matter. Okay. So, convection, basically hot fluids rise, cold fluids sink, and then you can transfer heat by the motion of the fluids. So we've gone from solids to liquids and gases. If you have here, like we have 2 cold coffee cups and a hot coffee cup, here's a bunch of water above them with some food coloring in it, and you can see above the hot coffee cup you have the fluid rising, and then over here where the water's cold it falls back down, and you get this nice circular-ish pattern. All right, and I just found this really fun GIF from the newwaveprooven.com as seen on TV. Okay, this is heat circulating. Okay, this is called forced convection. Why is it forced? Yeah, convection just means airflow, right? And forced convection means you're forcing the air to flow, so you're moving the heat around intentionally. It's also natural convection, which means there's heat going up and then cold air falls, and so you get circulation. It's much slower. And this is called a German pyramid. Anybody seen one of these? They're very popular with fancy older ladies during Christmas time. No? You guys don't have the same mother-in-law I do? Okay. So natural convection, you light candles on this thing. What happens with the hot air from the candles? Rises. What does it do to this? Spins it. Okay? And then you have like cute little angels and things that go in a circle. And if your mother-in-law is like my mother-in-law, she buys one of these she bought like a $200 one from Germany, and she was like, it's broken, it doesn't work. And it's because she put all her fan blades at random angles. And she was like Googling, like, how do I fix this thing because it's broken? And she was like trying to return it to Germany. And I was like, it works now. So anyway, you can be a hero at Christmas if you know physics. And then we have radiation. So electromagnetic waves are emitted by all objects. Actually, you are currently emitting electromagnetic waves. What range? What are those called? Somebody in the previous class said X-rays. I was like, and the guy sitting next to him like moved away because we just talked about the cancer thing. But no, are you cold, warm? You're emitting heat, which means that is infrared radiation. Okay, so you are emitting infrared radiation. You are actually what's known as a black body radiator, but we'll talk about that later. So anyway, if you look at infrared radiation maps, wait, why isn't this working? Oh, there it goes. Here, this is a glass of hot water. Here's a glass of cold water, so you can see this is where the water's hot. These look the same. You can't even see the water, and you can't tell what temperature it is by looking at these cups, although the hot one is red. But here you can see the water looks dark. Here the water looks bright. This one's hotter. Okay. Can you see this guy's hand? No. But if you look at an infrared map, even though there's plastic which blocks the visible light, it does not block infrared. All right? What? Oh. That's great. All right. It turns out the rate of heat transfer for radiation is T to the fourth, so temperature to the fourth power. Okay, so Q is proportional to T to the fourth, and the frequency is proportional to the temperature. Okay, that's the frequency of the wavelength. I just want to warn you before I start this video that I think it was made in either the late 90s or the early 2000s, so it looks a little dated, and somebody got really excited that they could do transitions in the video between scenes, and the graphics are what you would expect for that era. But it's a good video, so we're going to watch it anyway. No, nobody's made a better one that's less cheesy.
These days we're all familiar with night vision cameras, but how do these things work? How is it that you can just turn on this camera and see the invisible? Another use of night vision cameras that you might not be familiar with is their ability to see through smoke and dust. Fire departments commonly use cameras like these to find people trapped in smoky rooms, or to pinpoint the exact location of forest fires through clouds of smoke. So how do these things actually work? What are we really seeing when we look inside a night vision camera? Well, it may surprise you to learn that everything in the universe emits some kind of light. It's just not the kind of light we're used to thinking about. The sun, for example, our star, emits visible light. That's why our eyes evolved to detect that kind of light. But that's not the whole story. I'm sure you're familiar with all the different kinds of visible light, all colors from violet to red. But there are actually lots of other kinds of light that our eyes aren't sensitive to. The reason all the colors of light are different is that they have different energies. And what you see here is that the light has different wavelengths. The blue light, for example, has a higher energy, so it has a shorter wavelength. The red light, on the other hand, has less energy, so it has a longer wavelength. But that's just the light we can see with our eyes. That's not all there is. The shortest wavelength of light are gamma rays, which can have wavelengths smaller than an atom. The longest wavelengths are radio waves, which can have wavelengths larger than the entire Earth.
No, this worked like earlier today. Cool. That's fun. Sorry, I'll run it back a little.
You shouldn't have. That sort of light is called infrared light.
I don't know, she's chewing the mouth though.
It looks a lot different than infrared light. Remember that what you're actually seeing is temperature. Something that's warm is going to look bright in the infrared. And something that's cold looks dark. Ice cream.
What?
Blow dryer. And infrared radiation is actually a measurement of temperature. Places on my face that are cold, like my nose, appear dark in the infrared camera because they're giving off less infrared radiation. And places that are warm, like my mouth, or the hair next to my head, are brighter because they're warmer. You can even see my breath in my nose if you look carefully. And this is an ice cube. And humans, of course, are not the only things that emit infrared light. What do you think you can learn about animals by observing them in the infrared? What about reptiles? Remember, they're cold-blooded. Giraffes. Here's a Nubian ibex. What do you think horns look like in the infrared? Can you even see a gorilla in this picture? If you look carefully, you'll notice you can still see the zebra stripes even in the infrared. How about elephants? What about a polar bear? How about a rhinoceros? Check out the horns. All right, a cat. Notice the infrared footprints. Deer in the dark. A helicopter. Notice the plume of heat from the engine. Earth movers with hot smokestacks. A car engine turning on and heating up. Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light entirely. I have a black plastic bag, and as you'll notice, you can't see through it at all. But with an infrared camera, there's no problem. But just like infrared light can penetrate some things that stop visible light, it also gets stopped by some things that let visible light through. For example, here's a piece of glass. As you can see, none of the infrared gets through at all. If you haven't guessed, that's how the greenhouse effect works. Infrared light can't get through gases like water vapor in our atmosphere, which means that the heat is trapped and our planet is getting warmer. So what am I, an astronomer, doing with an infrared camera? Well, if everyday objects look different through an infrared camera, you can bet objects in space do too. For example, here's an image of the constellation Orion, which you're probably familiar with from the night sky. But now, let's look at it through an infrared camera. Look how much you're missing. Astronomers are also hoping to use infrared light to find planets around other stars. Planets don't give off any visible light of their own, making them nearly impossible to see close to a bright star. But in the infrared, planets give off their own light, making them much easier to find. Astronomers will soon be able to use very sensitive infrared cameras on a new space telescope, the Space Infrared Telescope Facility. And it gives a whole new perspective on the universe.
Yeah, it's like up there.
At that point, we're finally beginning a more complete view of the universe. Right now, we don't even know what we're going to discover. There are so many wonders out there. We'll finally be able to see more than our eyes can see.
The music is so good.
Music by Jeff.
I know. I
wonder if he's on the spot.
I can't remember what year this is from, but it's old. Yeah, so sorry about the production quality of that video, but aside from the two like modern applications, which are now like 20 years behind because that satellite went up that telescope went up a long time ago, and we found like literally thousands of extrasolar planets now, and the main guy who found them is super rapey. But he got fired a little bit. But he's still really good at finding planets. So I guess there's that. Radiation, just if you think about Earth, okay? Light comes in from the sun. It's mostly in the visible range, also a little bit of UV, which is why you have to wear sunscreen, a little bit in the infrared, okay? What gets through the atmosphere? Mostly visible and a little bit of UV, right? Even there is some stuff in the infrared range, and that bounces off. Okay, so if the Earth didn't have an atmosphere, this stuff would come in, it'd heat up the Earth, and then what does the Earth give off? Infrared, right? So the light hits the Earth, okay? It heats up things like water, soil, people. If you stand in the sun, you can feel yourself heating up, right? Some of the light just bounces off you, so visible light can just bounce off you, which is why I can see you, right? Visible light bounces off you, that's what we see. Some of the light gets absorbed, and that comes back out as heat, okay? So this is the energy radiated by the Earth. So the light hits the Earth heats up, it radiates infrared, okay? If you didn't have an atmosphere, the temperature on the surface of the Earth, based on energy considerations, like how much light from the sun hits the Earth, how much it heats up, would be about negative 22 degrees Fahrenheit. That would not be a very pleasant Earth to live on, so it's good that we have an atmosphere, okay? This is actually the temperature of the outer atmosphere, which is how we know that's true. You can check that, okay? You can send something up there with a thermometer and be like, okay, that's the temperature, okay? So outside the atmosphere, we're at about negative 22 degrees Fahrenheit, okay? If you put this back in, well, instead of escaping out into space, infrared doesn't go through the atmosphere. So it didn't come in from the sun, right? All the infrared bounces off coming in from the sun, but any infrared radiation we produce from the Earth, okay, gets trapped because it can't leave. So it just bounces around. And this is what we call the greenhouse effect, okay? Whether or not you're subscribing to climate change, this is just why the Earth is warmer than it would be without an atmosphere, okay? And the chemical composition of the atmosphere is what determines which wavelengths of light get through and which ones get trapped, okay? So if we change the chemical composition of the atmosphere, we change the balance of how these things work. And we can also create more heat in the Earth on our own by using other types of energy that aren't solar, like, you know, burning dead dinosaurs and things like that. And that changes the whole picture. But this is the basics of how it works. Like, for instance, Venus also has an atmosphere, but it's not a place you would want to live. Okay, it is a little bit closer to the sun, but it's significantly hotter, not in proportion to its distance from the sun. And it's hotter because its atmosphere is made of such a dense gas that a lot of light doesn't even get in, but light that comes in gets trapped forever. There's lots of heat going on, and it gets super hot under their atmosphere. Okay, so there's and then, you know, Mars has a very sparse atmosphere, so it's very cold. There's lots of different factors, but basically the wavelength of light matters. Certain chemicals, certain molecules absorb light or reflect light at different wavelengths. Okay, so the wavelengths that come in are not necessarily the same as the wavelengths that go out. Okay. Also, heat transfer in the human body. Remember, air is a poor heat conductor, okay? Water is also a poor heat conductor, but it's better than air, which means if you're in cold water, you die a lot faster than if you're in cold air. You can hang out in 45-degree weather, even naked if you have to, forever, essentially, without dying. But if you're in 45-degree water, you have about a couple hours. And if you drop that 10 degrees, you can get down to minutes, okay? 35 degrees is pretty cold. You might want a sweater if it's air. If it's water, you can die within an hour. Okay? So that, and there's some chart if you want to look at that.